Okay, so we'll get back to improper integrals. This is section 7.8. Now, remember that there's two kinds of improper integrals. One is where you have an infinite interval. So like, this example would be an example of the type 1 kind of improper integral. We'll look at 3 more examples of type 1 kinds of improper integrals. And the type 2 kind is where you have an infinite discontinuity, meaning a vertical asymptote is on the graph that you're integrating on. Okay, so what if we want to integrate x times e to the x going from 0 to infinity, going from negative infinity to 0? Well, that's a type 1 kind of improper integral. And so the first thing I do is I use the limit definition. Okay, so I'm going to say the limit as t approaches negative infinity, the integral going from t to 0 for x times e to the x dx. Okay, and I got x times a function, so that suggests that I'd want to maybe think of integration by parts for integrating. This one is going to require integration by parts. So if I let u be x and dv be e to the x dx, then I wouldn't have these switched, right? Because if u is e to the x dx, du is e to the x, or excuse me, if u is e to the x, then du would be e to the x dx. And if dv is x, v would be 1/2 x squared. Okay, so I just increased the power by 1 on this, and that doesn't help me at all. Let's see. The limit as t approaches negative infinity, and by the way, continue writing your limit notation. The limit notation must look good, okay? For u times v is x e to the x, and the definite integral, so I'm going from t to 0, minus the integral for v du, so minus the integral going from t to 0 of e to the x dx. Okay, the antiderivative of e to the x is itself e to the x. And so then the next thing I'm doing is I'm plugging in the bounds. So when I plug in 0, let's see, I'm going to have 0 on this guy right here, minus when I plug in t, I'll have a minus t times e to the t, okay, and then minus the antiderivative of e to the x itself, e to the x. So then when I plug in 0, e to the 0 is 1. Anything to the 0 power is always 1. Minus, plug in the lower bound now, be e to the t. Okay, so this is where I'm at right now. Okay, again, I'm writing my limit notation there. So now the first thing is the limit as t approaches negative infinity of negative t times e to the t. So I've got that shown down here, and you don't have to worry about the negative. That's not going to make any difference for the what we get there. But the limit as t approaches negative infinity of t times e to the t. I'm going to write that as the limit as t approaches negative infinity of t divided by e to the negative t. All right, so e to the t, that's the same as 1 over e to the negative t. And the reason why I did that is because now I'm in indeterminate form. Okay, so now I can use L'Hopital's rule. L'Hopital's rule is something that we learned in Calc 1. And so you can only use L'Hopital's rule when you're in indeterminate form, meaning that you're in the form of infinity over infinity or 0 over 0. Okay, those are the only two types of indeterminate form. So well, let's see, we're approaching negative infinity, right? So I'm going to have negative infinity divided by e to the, something that's growing without a bound is going to be something that's growing without a bound. So I'm in indeterminate form here, infinity over infinity. And that means that I can use L'Hopital's rule. So the capital H above the equal sign means that I'm using L'Hopital's rule at this point in the problem. We got the limit as t approaches negative infinity of the derivative of the top divided by the derivative of the bottom. The derivative of t is 1. The derivative of e to the negative t is negative e to the negative t. Okay, and then when I calculate this limit here, t is approaching negative infinity. Right, so I got 1 divided by negative e to something that's growing without a bound is going to be something that's growing without a bound. There's a negative in front of that. So I got 1 divided by some negative item there that's growing without a bound. Well, that's going to become 0, right? Because the numbers are going to be getting very minuscule negative numbers, and they're going to be, getting closer and closer to 0. Okay, so this limit is going to be 0. Okay, minus limit of a constant is always the constant, and then negative times negative is positive. The limit as t approaches negative infinity of e to the t, well, that would be 0, right? Because the limit as t approaches negative infinity of 1 divided by e to the negative t is 1 divided by something that's growing without a bound, meaning that the corresponding numbers there are going to be getting very minuscule, getting very close to 0. Okay, so that's me 0, and I get -1 as the answer. Okay, so this would be a convergent integral here. Again, the reason why I'm saying it's convergent is because I get a number. Okay, it doesn't matter positive or negative. The reason why that's a negative is because, if I look at this curve, y equals x times e to the x, going from negative infinity to 0, that entire curve is going to be below the x-axis. So the area is a negative number. Okay? Again, a divergent integral means that you're going to get infinity or negative infinity, or it does not exist. Okay? It's not going to be some number there. Let's try another example. So what if I want to find the integral for 1 divided by 1 plus x squared dx going from negative infinity to infinity? Okay, this is an improper integral. So, and I'll need to split this at a number. Okay, now I can choose any number I want. I selected 0 because the antiderivative of 1 divided by 1 plus x squared is tangent inverse of x. And tangent inverse of 0 is 0. Okay, so it's going to be most convenient for me to split this at 0 rather than some other spot, although I can, split it at some other spot if I want to. The point is that I have to split the integral. Okay, and so let's look at this integral here first. So the integral going from 0 to infinity of 1 divided by 1 plus x squared dx, that is the limit as t approaches infinity of the integral going from 0 to t of 1 divided by 1 plus x squared dx. Okay, use the limit definition there. And the antiderivative of 1 divided by 1 plus x squared, that's tangent inverse of x. And I'm going from 0 to t. So then when I plug in my bounds, plug in the upper bound first, I got tangent inverse of t minus tangent inverse of 0. We want the limit as t approaches infinity of that. Okay. Now tangent inverse of 0, well, here's the graph of the tangent inverse curve. I would highly recommend knowing the graph of the tangent inverse curve. You're going to use it a lot. Okay. Let's see, tangent inverse of 0 is 0. Okay. So the only thing I need to do here is I need to find out the limit as t approaches infinity of tangent inverse of t. Okay, well, the tangent inverse curve has 2 horizontal asymptotes on it. One of them is at pi over 2, the other is at negative pi over 2. So as I head outward towards infinity here, this graph is getting closer and closer to pi over 2. Okay, so pi over 2 would be the value of that integral. And I got this other integral here that we got to find. So I got my work shown down here with that one. The integral going from negative infinity to 0 of 1 divided by 1 plus x squared dx. So use the limit definition. That's the limit as t approaches negative infinity of the integral going from t to 0 of 1 divided by 1 plus x squared dx. And that's the tangent inverse function, right? So let's see, when I plug in my bounds, plug in the upper bound first, I got the limit as t approaches negative infinity of tangent inverse of 0 minus tangent inverse of t. Okay, well, tangent inverse of 0 is 0. Okay, and now I'm approaching negative infinity. So as I approach negative infinity here, the corresponding y values are getting closer and closer to negative pi over 2. Okay, so I'm going to have a minus negative pi over 2. That's positive pi over 2. Okay, and the value then of this integral would be where I take pi over 2 and then plus pi over 2 gives me pi. Okay, so so pi is the area under the curve on the entire interval, is what we're saying there. Okay. Let me show you one more kind of improper integral here. So I can't emphasize enough the notational part of this. Okay, students lose ticky-tack points because of notational errors. Don't do that. Okay, we need to write the limit notation, and if there's a u substitution, we need to make sure that everything involving u is part of the new integral. You never want to max u and t or u and x or whatever. Okay, that'd be bad, and that'd be wrong. Okay, so let's see. Let's do this example next. So I want to integrate going from e to infinity 1 divided by x times the ln of x dx. Okay, that's a type 1 kind of improper integral. So I use the limit definition. That's always the first thing that I'm doing here. So I got the limit as t approaches infinity of the integral going from e to t of 1 divided by x times the ln of x dx. Okay, and let's see. So you can use the u substitution on this. If I let u be the ln of x, du is 1 over x dx. I got a 1 over x dx inside the integral. Okay, so I'm going to be integrating 1 over u du. Now again, everything about my integral has to be in terms of the new variable, u. So the bounds right now are in terms of x. Okay, if x is t, the upper bound is going to be the ln of t. And then if x is e, the lower bound, the ln of e is 1. Okay, so I'm going to be going from 1 to the ln of t on this new integral here. Okay, well, that's going to be the limit as t approaches infinity of the ln of the absolute value of u, and I'm going from 1 to the ln of t. So then plug in the bounds there. I have the limit as t approaches infinity of the ln of, the upper bound is the absolute value of the ln of t, and then minus the ln of 1, that's 0. Okay, so I'll be subtracting 0. And t is approaching infinity. Okay, so the ln of t would be also approaching infinity, and the ln of something that's growing without a bound is something that's growing without a bound. So we get infinity as the answer there. Okay, that's a divergent integral. So, the area under the curve is going to be in infinite region, okay, meaning that it's divergent. Okay, so we'll go ahead and we'll stop right here, and then in the next video I'm going to talk about the type 2 kind of improper integrals where you have a discontinuous integrand. Okay, or a vertical asymptote is somewhere on the interval that you're integrating on. Okay, so we'll go ahead and stop right there.